welcome back to another Gregorius Maths video. In this video, I'm going to be continuing on with my classical homotopy theory series, and well, yeah, I'm just going to be moving on straight away to defining and talking a little bit about the basic properties of homotopy groups, which are obviously going to be the main thing that the main object that we're going to be studying throughout the series. And by the way, about the blog posts, I'll probably be producing blog posts with extra remarks and stuff slower than I'll be producing videos. So every time I make a new blog post, I'll just, I'll do a community post or something to notify people, and I'll put it in the description of the video that's for. But okay, so with that in mind, we're going to be moving on straight to defining and talking a little bit about higher homotopy groups. And before I talk about that, might as well motivate this a little bit. Well, the reason that we want to do this is to try and classify spaces up to some sensible form of equivalence. So in topology, it's normally homeomorphism, and higher homotopy groups help us do that, and they help us with the goal of classifying spaces up to homotopy equivalence too. Also, homotopy groups of spaces can tell us information, and it can help us decompose different spaces up to homotopy, and so on and so forth. Of course, these things are not simple to compute in general. For example, homotopy groups of a relatively simple space such as the sphere, computing those things, even though computing homology, for example, or cohomology of spheres is a pretty simple problem, computing homotopy groups of spheres is a classic problem in homotopy theory. These things are not that easy to compute, but they're really useful when you can. So, alright, let's actually define what the homotopy group of space is. So, let's say we have a based space. Given a based space X with some base point x0, we can define pi n of x with some base point x0. We define the nth homotopy group of x to be the set of homotopy classes between the n cube, which is just the boundary multiplied by itself n times. Basically, it's the set of homotopy classes of maps, based homotopy classes of maps between this pair and x, x0. And this should probably be a comment, shouldn't it? Alright. So, this is our original definition, and, well, the reason that we call them homotopy groups is they do indeed form a group, and the first theorem we're going to prove is that they form a group. But how exactly do they form a group? Well, we define f star g of, say, S1 up until Sn to be, so firstly we'll have f of 2S1, and then we'll just have up until Sn for S1 between 0 and a half. And then we'll have g of 2S1 minus 1 up until, and then we'll just have Sn for S1 between 1/2 and 1, like so. Alright. Okay, so the first thing we'll show is that this is that pi n is a group, and of course it's a well-known thing to say that pi n is an abelian group if n is bigger than or equal to 2, and I'll just give an intuitive explanation as for why n must be bigger than or equal to 2. Alright, so the first theorem we'll prove is the following theorem. pi n, so for any space x, pi n x 0 is a group for n bigger than or equal to 1, and it's abelian for n bigger than or equal to 2. Okay, so we're going to prove this, and the only real explicit calculation that I'll do is for associativity, because for inverses and for the identity, I'll just tell you what the inverse of a function is and what the identity is, and then I'll let you check those by hand. Alright, so for the abelian point, well let's, okay, so remember that In is an n cube, so I2, I squared, will just be a square. So let's deal with that for the moment. So let's say we're working in here, and we have F, we have G. Well, this picture here, this is going to be homotopic too. Now, up to homotopy, we can shrink F down to be a square like this, and we can make G this. And this is homotopic too. Now let's slide both of them across. So we'll have G over here, and we'll have F over here. So what we're doing is, we shrink them down, we slide them past each other, and then let's just stretch them back up. All of this is up to homotopy. So we've shown with these pictures that you can interchange these two maps. And of course you won't be able to do this when n is equal to 1, because there's no way that we can go up when we're just dealing with a one-dimensional thing. Alright, so okay, let's just let's just show what the identity and inverses are, and then we'll go on to associativity. So the identity is given by sending In to just the base point, and the inverses, well, the inverse of f of s1 up until Sn is equal to f of 1 minus s1 up until Sn. Okay, so now what we're going to do is we're going to show that this operation is associative. Obviously, what does this mean? Well, this means that alright, so means that f star, and then if we do g star h of some s1 up until Sn, this must be equal to, homotopic to f star g star h of s1 up until Sn. So we're just going to compute this explicitly, and that should be that. Okay. So first we'll compute this, then we'll compute this, then we'll construct a homotopy between the two. Alright, so firstly, f star g star h of s1 up until Sn is equal to, so on top what we're going to have is, well, by definition we'll have f star g of blah blah blah, so we'll have f star g of 2s1 up until Sn, when s1 is between 0 and a half. We'll have h of 2s1 minus 1 up until Sn for s1 between 1 half and 1. Now, of course, we can also expand that f star g. So let's do that. This is equal to f of, and then what we're going to have is we're going to have 2 times 2s1. So it's going to be 4s1. And then again we're going to go up until Sn. And this time we're going to have s1 being between 0 and 1/4. Now, the g will be 2 times 2s1, which will be 4s1, and then minus 1. So we'll have g of 4s1 minus 1 up until Sn for S1 between 1/4 and 1/2. Then on the bottom we'll still have h of 2s1 minus 1 up until Sn for S1 between 1/2 and 1. Okay, so that's that. Let's just leave that for now. And let's compute the other one. So that is, what is f star and then g star h. Let's compute that. So we'll have f star g star h of S1 up until Sn. That's equal to, we'll have f of 2s1 up until Sn for S1 between 0 and 1/2. And on the bottom we'll have g star h of 2s1 minus 1 up until Sn for S1 between 1/2 and 1. And again, that's by definition. So, what do we do next? We expand the bottom, and then we get two piecewise functions which each have 3 components, f, g, h, in that order. And then we'll just we'll do a homotopy which is also piecewise, which will be a homotopy between the top of this, so it'll be a homotopy between that, and then whatever g and h turn out to be, we'll get a homotopy between g and h and h. So let's see what we need to do, and then we'll try and do it. So this is equal to, again we'll have f of 2s1 up until we'll have f of 2s1 up until Sn for S1 between 0 and 1/2. We'll have g of, now this is where it gets a little bit more tricky. We need to do 2 times and then all of this, so 2s1 minus 1, and that's 4s2 minus 2. So we'll have 4s2 minus 2 up until Sn for S1 between 1/2 and 3/4. And we'll have h of, and then we'll have this minus 1, which is 4s1 minus 3 up until Sn for S1 between 3/4 and 1. Okay, so what I was saying before basically is we need to construct a homotopy between this piecewise function here and this piecewise function here. Now, of course, the way that we're going to do this is we're going to construct a map such that at the time t equals 0, we get 0/4, and then at t equals 1, we get 0/2 for the interval. And also we need to go from 4 to 2. So that's the first part of this piecewise function. So we'll have h of S1 up until Sn t being, now what are we going to have? Well, to get from 4 to 2, we're just going to have f of 4 minus 2t S1 up until Sn for S1 between, okay, we'll just leave the interval for now. Why does this work? When t equals 0, we'll get 4s1. When t equals 1, we'll get 2s1. Okay. Now we need to go from 4s1 minus 1 to 4s1 minus 2. So we'll just have 4s1 and then minus brackets, and then we just need to go from 1 till 2, which is easy. You just do 1 plus t. So we'll have g of 4s1 minus, and then we'll have 1 plus t up until Sn for S1 in, and again we'll deal with the intervals later. And the reason this works is, of course, we'll have 4s1 minus 1 when t equals 0, precisely that, and we'll have 4s1 minus 2 when t equals 1, which is precisely this. Now, it's a little bit trickier, but it's still definitely not impossible. We need to go from 2s1 minus 1 to 4s1 minus 3. So how do we do this? We'll have h of, so first let's go from 2 to 4. To do that, we'll just do 2 plus 2t. So we'll have 2 plus 2t times s1, so that when t is equal to 0, we'll have 2s1, and when t is equal to 1, we'll have 4s1. And then minus, well, now we need to go from 1 till 3. And the way to do that is, we'll have 1 plus 2t. And then up until Sn for S1, and then we'll worry about the interval a little bit later. And why does that, is that what I had here? Yeah, that's what I had here. And of course the reason that this works is because when t is equal to 0, we'll have 2s1 minus 1, which is precisely this. When t is equal to 1, we'll have 4s1 minus 3, which is what we have there. Okay, now I've ignored the intervals, but we need to deal with them. So, we need to go from 0 to a quarter to 0 to a half. The way we do this is, well, we use this, so obviously we're going to have 0 in both cases, so we'll put 0 here. And the 1 quarter needs to become half, so we'll have 1 over, we just need to go from 4 till 2, which is easy, you just do 4 minus 2t. Now, okay, so that interval is not too difficult. This interval is slightly more difficult. We need to go from 1 quarter to 1 half, and a half to 3 quarters. So, we're going to write, so, we just need to add a quarter on, really, to both of these things. So, what we'll have is 1 quarter plus t over, okay, let's write this out. 1 quarter plus t over 4, and then we'll have 1 half plus t over 4. But, okay, so then when t is equal to 0, we'll get a quarter, a half. When t is equal to 1, we'll get a half, 3 quarters. So it's that, but we can write this all out as one fraction. That's not difficult at all. The first part will be 1 over 1 plus t over 4. And then the second part will be 2 plus t over 4. Like so. Okay, and is that what I had here? Oh, I had a slightly different version. I had, let's see what the I had 1 over 4 minus 2t, so I went from a quarter to a half by subtracting from the denominator, because it's just going from 4 till 2, but I kind of prefer this version because I'm going up. I'm just going up by a quarter, and this one works fine too. And then the last one will just have to go from a half to 3 quarters, and 1 stays the same, so it's the same deal. We'll just have 2 plus t over 4, 1. Like so. And that's our homotopy, which is between f star and then brackets g star h and f star g bracket star h. So that's our proof of associativity, just to get a feel for how this operation works. Okay, now we've shown that our pi n is a group. So what we're going to do is we're going to switch up a little, and we're going to look at it from a different perspective. And the perspective that we're going to take a look at now is going to be our definition for pi n for the rest of the series. I'm pretty sure. So let's take a look. So excuse me. A map. Alright, so what did I say? Yeah. Maps from this pair here to there are the same as, and then what we're going to do is we're going to quotient both things in this pair by the boundary of In. So, as maps from In mod the boundary of In, comma the boundary of In modulo itself, to x 0. And this is equal to, well, In modulo the boundary of In is equal to Sn, and then we're just going to pick a base point S0 to x 0. And this is a more neat definition if you ask me. So, really, what we're dealing with here is based homotopy classes of maps between the n-sphere and x. And again, we're taking the base point to base point. And the new operation is given us the following composition. So, f star g is the composition where we go from Sn to Sn wedge itself via the map C, which collapses the equator in Sn. In Sn. Then we're going to go via f wedge g to x wedge itself. Okay, no problem there. And then we're going to go via the fold map down to x. So f star g becomes this new composition here. And it's still a group and it still works the same way. It's just it's just different it's just a different operation. Alright, okay. So that's just the perspective which we're going to be looking at it from. So to conclude, pi n is the set of based homotopy classes of maps between the n-sphere and x, and it's got a slightly funky operation in this. Alright. Oh yeah, and also, we need to take a quick detour, because of course this is still pi. Let me just look at this. You see pi n x 0. Well, when do we actually need to specify the base point? And I'll prove this in a later video. It requires slightly more advanced machinery. But the theorem is that when x is path connected, we have that pi n of x at x0 is isomorphic to pi n of x at some other base point x1. So from now on we're going to assume that our spaces are path connected, and we'll just write pi n of x. Alright, so we haven't looked at anything categorical so far, and what I'm going to do is I'm going to show that pi n is a functor from top to group. So it does take in a topological space and output us a group. We've already shown that. What we need to do is define is first of all we need to see what it does to functions, continuous maps, and then we'll show that it respects composition and so on and so forth. And actually it's quite a useful fact because it allows us to show an important property of fundamental groups. Yes. So what we're going to be talking about is a notion called the induced map. So, definition. Yeah, okay, so given a map, phi, and it's a based map between base spaces, x and y, we'll define the induced map, phi star. What's it going to do is it's going to go from pi n of x at x0 to pi n of y at y0. What's it going to do? It's going to send the class of some map f is going to be mapped to the class of phi composed with f. Yeah. Yeah, okay. So this is how it's defined. So it's the induced map, and it's quite a natural definition. Good thing about it is that it satisfies some very nice properties. So, firstly, and we're going to prove them. Alright, so theorem is that it satisfies that phi psi, for example, star is equal to phi star psi star, and the identity star is equal to the identity. Alright, so let's prove these, and the proofs are really simple, and then I'll go on to show what these actually mean categorically speaking. Alright, so I'm kind of disguising a certain proof, which will become clear in a second. Sorry, I'm disguising a certain theorem, which will become clear in a second. So, really, you just apply the definition. Simple as that. So, phi psi star applied to some class of f is equal to, by definition, it's equal to the class of phi psi f. And this is equal to, we can take this phi out, phi star of psi f, and then we can take the psi out to make the phi star psi star f, like so. And that just comes straight from the definition, so it's nothing too complicated there. And secondly, second part of the proof goes as follows. Well, we'll just do, okay, so the identity star applied at some f is equal to the composition of the identity with f, and it's just equal to the class of f as required. So that's a very simple proof. Alright, so what does this actually mean though? And, well, I'll tell you what it means. Let's say, for now, let's just call phi star pi n of phi. That's just a notation change. It's not changing the definition, it's just notation. What are these things now saying? This is saying that pi n of phi psi is equal to pi n of phi composed with pi n of psi. And this is saying that pi n of the identity is equal to the identity at pi n. And we'll just say the identity at x and pi n of x. So, if you watched the last video or are familiar with functors, this should ring a bell. Namely, the bell that it should be ringing is, well, this definition of a functor, right? It respects composition and it respects the identity. And indeed it does. So what we can really say is that pi n is a functor between based topological spaces and groups. Okay, And one thing I shall say is I'll prove the following lemma actually. What colour should I use? I'll use purple. Alright, so the lemma is basically that homotopy equivalent spaces have isomorphic fundamental groups. Alright, so lemma. What do we have? Well, we have that if x and y are homotopy equivalent, then pi n of x is isomorphic to pi n of y. And the proof is fairly simple. Let's say that we have phi going one way. So let's say we have phi from x to y and y from, and some psi from y to x. Now, by definition of homotopy equivalences, the composition is homotopic to the identity. And therefore, what we have is that the induced maps phi star from pi n of x, x0 to pi n of y, y0, and psi star from pi n of y, y0 to pi n of x, x0 are inverses. So the way we do this is phi star composed with, does that work out? Yeah, phi star composed with psi star is applied to some f. This is equal to the class of phi psi f. This is equal to the class of, well, composition is associative, so we can do phi psi first, and then we can do f. And this is equal to the class of f. The reason for this is, well, remember that this composition here is homotopic to the identity. Now, these are homotopy classes of maps, so of course their composition is going to be in the class of the identity. And therefore, these two maps are inverses. These two maps from pi n of x and this map going this way are inverses. They're homomorphisms too, because pi n is a functor and whatever. And therefore these two groups are isomorphic. So that's a neat little property which we can use these things for. Now, a couple of other things I'll say, because it'll be awkward to write them down and then, so I'll just say them. Firstly, if x is contractible, then it has trivial homotopy groups, and that is obviously because pi n of this point is trivial, and contractible by definition means homotopy equivalent to a point. So therefore, stuff like the real line is has trivial fundamental group. Also, we have that pi n respects products. So, pi n of a product of spaces is isomorphic to the product of those pi n's. And there's a slightly deeper result about covering space projections, which is that if we have a covering space projection, then the induced map of that covering space projection is an isomorphism on homotopy groups when n is bigger than or equal to 2. So, for example, this shows that pi n of the circle is 0 when n is bigger than or equal to 2, because, well, it's because the covering space projection, we can go from R to the circle, and obviously the homotopy groups are trivial. Alright. I'm just going to see what we're going to talk about. Oh yeah, relative homotopy groups. So, Next, we're going to talk about relative homotopy groups. Now, you won't see these things be talked about often, but they are still useful to know because we're going to be using them fleetingly in the earlier stages of this series, and that is to basically kind of replace them with other homotopy groups. Because they fit into a nice long exact sequence, so when we are able to replace that part of the long exact sequence with a homotopy group itself, then it's just more neat than having to stick in this other group, which we don't really care about that much. Still though, they of course are useful to know about, so I will talk about them briefly. Alright, so firstly we'll start with definition. We define P of X star A is the space of paths in X that start they start at the base point and they end in A. Okay, so that's our definition. Okay, what I'll just state is the definition, the much neater definition, and then I'll state the long exact sequence that they fit into. I won't state what the maps are or anything like that, but I will of course post these notes, and the details of this long exact sequence are in the notes, but I just don't think it's that crucial for me to explain them right now. So, let's actually define what the relative homotopy group is. So definition, pi n of x a and some base point star is equal to pi n minus 1 of this space here. Like so. So, that's basically our definition of the relative homotopy groups, and the reason that they're useful, or the reason that I like to think they're useful, is, of course, because of the long exact sequence that they fit into, and in our vibrations video, which will be an important video, where we'll prove quite a few things that we take for granted here, we'll talk about how we can replace the relative homotopy group in the long exact sequence by a different homotopy group, and obtain a long exact sequence of purely homotopy groups. So this is an important one to know. Okay, so the long exact sequence they fit into goes like this. So first we'll have pi n of a, and by the map basically just induced by the inclusion, we'll go to pi n of x, and then we'll go to pi n of x a, and this is induced by the inclusion of x and the base point into x a, the pair. Then we'll go via some connecting map, which I won't talk about now. And we'll go down to pi n minus 1 of a, and we'll keep going on like that. So that's the long exact sequence they fit into. That's really all I have to say about relative homotopy groups though. But you know, yeah. Okay. Let's just look at some, okay, I might as well tell you what the plan is for the rest of the video. The plan is to basically talk about a couple of computations of some homotopy groups, and then what we'll do is we'll talk about Eilenberg Mclean spaces, And then we'll talk about how, Eilenberg Mclean spaces are connected to cohomology, and then that's basically what we'll do for now. So, still quite a lot of interesting stuff to cover. The computations that I have in mind are just not very complicated things, just a couple of examples. That's theorem. We have that, firstly, pi I of the n torus, that is n copies of the one sphere, is equal to, first we'll have n copies of the integers when I is equal to 1, and we'll have 0 otherwise. We also have that pi n of the infinity sphere is equal to 0 for all n. Now, these follow from some very simple properties of homotopy groups. This one here follows because pi I of the circle is given by the integers when I is equal to 1 and is trivial otherwise. So by the fact that these homotopy groups respect products, what we have is, we'll just have n copies of the integers when I is equal to 1 this time, and we'll have 0 otherwise. And this result here follows because the infinity sphere is contractible. Okay. Okay, so Eilenberg Mclean spaces. These are the last things we're going to cover, and again, they're very interesting things because of their connection to cohomology. So they stem from these homotopy groups, and their definition is elementary enough so that just knowing what a homotopy group is enough to define them. All right, so. So, definition, and this is quite a natural definition actually, when you see it. Given a group G, the Eilenberg Mclean space, of type K of Gn is a space such that pi I of K of Gn is equal to it's equal to G when I is equal to n and it's 0 otherwise. These things are unique up to weak homotopy equivalence. Also, may I say an example of one of these? I don't know if yeah. Yeah, okay. An example, so we actually have some very interesting spaces which are examples of Eilenberg Mclean spaces. So the first example, of course, is the circle. So we'll have that the circle is equal to K of Z1. And of course the reason for this is because pi I of the circle is equal to the integers when I is equal to 1. And it's 0 otherwise. Now, the infinite lens space, and I'll talk about this in a minute, L infinity P is equal to K of this finite field 1. And what it actually is it's equal to the infinity sphere mod this finite field Fp. Okay. That's a very interesting space. I think it comes up in physics somewhere. Probably does. And, you know, we won't really talk about... I might compute the cohomology of it really later on with the spectral sequence or something. But it's just an interesting space to know about, you know? And also, an interesting example is CP infinity is an Eilenberg Mclean space. So K of Z2 is equal to CP infinity. And actually, there's a... Also, Eilenberg Mclean spaces satisfy the property that... How should I put this? The loop space of... Let me write this out to check that it works. The loop space of... Yeah, I'll write it here. Actually, no, I'll write it... Deary me, I'm a bit clumsy today. The loop space of K of G N is homotopy equivalent to K of G N minus 1. Is that right? Because when we apply... Yeah, this is right. Reason for this? It's actually, well, not the reason, but a sanity check to check that this is right. When we apply pi... Oh god, you don't even know what a loop space is yet, if you're following the series. Okay, when we look at loop spaces, we'll look at this result. Yeah, gosh, what was I thinking, yeah. Okay, it's a neat result, either way, but, okay, we'll look at it later. My bad. Okay, the last theorem that I wanted to state, anyway, was the connection to cohomology. And that is the set... And this is actually really shocking. I mean, I'd never expected this when I first saw it, but you know, it's a really cool result. And that is the set of based homotopy classes maps between between X and K of Gn is in bijection with the nth cohomology group of X with coefficients in G. So that's a pretty amazing result, if you ask me. And that's the last thing I wanted to state. So some closing remarks is that pi n is a functor from base spaces to groups. Pi n is invariant under homotopy equivalences, and it determines a class of spaces K of Gn, which are, you know, unique up to weak homotopy equivalence anyway, that have this connection to cohomology there. And yeah, that's all I had to say about homotopy groups for now. Of course, the whole rest of the series will be me talking about homotopy groups in one way or another. But for now, these are just the basic definitions that I wanted to lay out, and some examples and so forth, just to get a feel for what we're going to be dealing with. And, you know, of course, so that I don't have to waste time in other videos defining stuff that, you know, I can put here. So yeah, that's everything for this video. I believe that the next one will be about loop spaces and suspensions, and again, you know, if there's anything not correct or confusing about this video, do not hesitate to comment below. Okay. Yeah, goodbye. Thank you for watching, and, you know, stay tuned for the next one in the series.